Hello and welcome to Lecture 8 of Math 2R03. In today's lecture, we're going to look at dimension, which is actually one of my favorite topics in linear algebra. So our goal today is to introduce what the dimension of a vector space is, and one way to think about it is it's the size of a vector space. So we want to look at what this dimension is first, and then we're going to kind of link dimension with both linearly independent set, a spanning set, and a basis. And I also hope to do kind of a complicated example. So this is a topic we did see in Math 2R03, sorry, 1B03, but today we're going to kind of work through all the details that we might have skipped in that previous course. So let me make myself disappear. We have a nice little comic here for you to chuckle over while I write out the proof to our first theorem. So for our first theorem here, it's kind of important because it allows us to define dimensions. First, let me state what the theorem is. So let's say we have a finite dimensional vector space, and let's say that we have two bases, V1 through VP and W1 through WR are bases, our vector space. Then what we have is that the number of elements in the bases have to be the same. This P and the R is the same. And the proof is pretty straightforward. It's only two lines, right? And it goes as follows. Since V1 through VP is linearly independent, and because V is equal to the span of the vectors W1 through WR, then P is less than or equal to R, because this is something we proved earlier, that the length of any linearly independent set is less than or equal to any spanning set. But now that here I'm using only the linear independent property of the first set, and I'm using the spanning property of the second set. But now we can just reverse the role of these two things, and we get R is also less than or equal to P. Okay, so by the same argument, R is less than or equal to P. So there we have a two-line proof for this fact. So why this is important is because even though bases are not unique, so it's very easy to find a vector space and find many different bases of a vector space. What is unique is the number of elements in your basis. And because we have a unique number attached to that, what that means here is this very important consequence is that all bases of V have the same size, okay, have the same number of elements. Now, because they always have the same size, we can actually give a name to that number, and that's what the dimension of your vector space is. So the dimension of a finite dimensional vector space is the length of any basis of V, and this number is denoted dim, short for dimension, V. Right? The previous theorem says that once you find a basis, all bases will have the same length of the basis you find. So because of that, and because we've computed some basis for some vector spaces, we can actually compute the dimension of some vector spaces we've seen in this course so far. So the dimension of Fn is going to be n, because we know that there's at least one basis with n elements. The dimension of the empty set is going to be 0. Okay, and the reason for this is that due to the fact that the span of the empty set is equal to the vector space 0, and the dimension of our set of polynomials of degree m or less is equal to m plus 1, because a basis for this space is 1. Okay, maybe I'll write this down for your notes. Since 1z up to zm is a basis. Okay, so here we have a number attached to a finite dimensional vector space. So we've actually used the word finite dimensional just to mean that there's a finite set of elements that span our vector space, but now we can talk about the dimension, which is a number attached to a finite dimensional vector space. And it's kind of a measure of the size of your vector space. And one thing that we get here, and this should be kind of obvious if you think about it, is if you have U is a subspace of our vector space, then U is sitting inside of V, so we should expect that the dimension of U should be less than or equal to the dimension of the vector space V. Okay, again, it's trying to capture the notion of size in a vector space. And the proof here is it goes as follows. What we do is as follows. Let U1 through U2t be a basis of U. We know that since U1 through U, maybe I shouldn't say since, I should say then, we know that U1 through UT is linearly independent in V, and then let W1 through WP be a basis for V. So we have that P is equal to the dimension of V. And then what do we know? We've proved earlier that any linearly independent set, the number of elements in that set is less than or equal to the size of any spanning set. So then we get that T is less than or equal to P. Okay, and T is the dimension of U. So we have, maybe I'll put that in, the dimension of U, which is T, is less than or equal to P, which is equal to the dimension of V. So that's what dimension is. And what we're going to go into the next part is we're going to connect the notion of dimension, span, and linear independence. So I'll see you in part 2.